Welcome, astronomers. I hope you all had a great weekend. If you haven't seen your score yet, all of your scores are recorded. You all did very well on the midterm as a class. The average was 83%. Excellent job. The high score was 41 out of 40 with the extra credit. So y'all basically killed that exam. So good job. Hold on a second. Somebody's having trouble logging in. You can, if you have any questions on the grading, you can go and look at the, you can see what the correct answers were for the multiple choice. Yeah, I mean, nobody really, there was not one question on the short answer that you all missed. So if you have a question about it, you can either ask me now or send me an email. There was really no issues with it. So your score in D2L now is your midterm grade. Again, the class is doing very well. There's a few of you who I know can do better. It's really not, nobody's really not doing well on the assignments they do. Just some of us aren't doing all of our assignments. So if you do not like your grade, your midterm grade, do some work. That's all I have to say about that. Any questions or comments about that or anything else before we get started in our new subject? You all hear me? We all good? Okay. Okay, cool. Well, one of you can hear me anyway, so I assume you all can. You're missing some quiz grades. I don't think so, but send me an email on what quiz grades you think. Yeah, send me an email. Okay. Okay. Let's get started on our exciting topic. Tonight. I mean, all our topics are exciting, right? But this one I particularly love because when I was your age and I was just studying astronomy and astrophysics, we didn't know these things existed. These things being exoplanets, planets outside of our solar system. We knew they should exist because remember, one of our principles, our cosmological principle, is that the laws of physics are the same everywhere in the universe. And so we learned the laws of physics on how we make planets and how we made star systems. But we didn't have an experimental verification of a planet outside of the solar system. We do now. But it's a relatively recent development. So that's what we're going to talk about tonight. Let me get my screen going. Hold on, I need to share that differently. Stop. Okay. Exoplanets. They sound like superheroes, right? Some kind of X-Men or exoplanets. But the exo really just means, I mean, some of them are super. We actually call them super Earths. But the word exoplanet, the exo just means outside of our solar system. I want to give you a heads up for every image I'm going to show you tonight is an artist's rendition of a planet. I will show you some actual images of exoplanets on Wednesday night. I've actually already showed you a couple. But our technology is not good enough yet for them to appear like anything other than blobs. and if that. So what am I showing you then today? They are, it's an artist's rendition. It's not, it's a kind of a, it's not like an animation or something, or the animation is not the right word, but it's not like these artists just made them up. These are representations of all the things that we know about these planets. We know their sizes, we know their masses, we know their temperatures, we know the composition of their atmospheres without actually, a lot of that is by analyzing the light, but not all of it is. We'll learn all the different techniques, and all, which each will tell us about a planet on Wednesday. We're just going to kind of go through the menagerie of the exoplanets that we've discovered so far tonight. So take these with a grain of salt. They're not actual images, but they're also not just imagination. They are using all of the scientific measurements we've made about a planet to kind of make a hypothesis of what they would look like. And so you can see there are, these aren't even all of the planets that we've discovered. We've discovered over 4,000 exoplanets. They come in a wide variety of masses and temperatures and orbital configurations. They don't all just orbit stars like our sun. They orbit many, many different kinds of stars. The fact of the matter is that the stars that we are able to study, which so far are just the stars in our own galaxy, with this technology, more than 70% of them actually have at least one planet. And so that is astounding in itself. And then when we think about and we learn about how incredibly difficult it is to discover a planet, for us to have actually just get a number this high, that probably means that they all do. It's incredibly hard to find a planet. And so the fact that we can find 70% of them kind of implies that they probably all have them. I'm sure there's a star out there somewhere that doesn't have a planet, but it's already few and far between those that don't. And so, but we know at least 70% of them do. You can keep track of that a couple of ways. And in fact, if you haven't picked out your exoplanet to blog about this week, here's a couple of places to find them. Actually, I'd suggest you look down here. You can just Google exoplanet, Google weird exoplanet or interesting exoplanet, or whatever. If you want to do Earth-like exoplanets, Google that. We have discovered more than 4,296. I just copied this afternoon. That have been confirmed planets outside the solar system. We have a brand new space satellite, relatively new. It's actually not brand new. It's been up there for a couple of years now. That has confirmed 81 of those. And that satellite has another more than 2,000 that need to be confirmed. There's actually another couple thousand from the satellite that was up before this called Kepler that need to be confirmed. And so we have more data now it's a backlog of us able to look at all of that data and confirm. When I say a confirmed exoplanet, it means that we have discovered it in two of the different methods that both corroborate with each other that say that, that there is a planet there. You can kind of see from the headline here, we just discovered 4 new ones. I don't, what is today? 4 days ago. It turns out about every week we discovered a handful of more of these exoplanets, either by new measurements or by analyzing the data from these dedicated space telescopes that search for planets. TESS is the one that's up there right now doing most of the work. Okay, we found some surprising characteristics of these extrasolar planets. Many of them have highly elliptical orbits, kind of like Pluto. In fact, there are entire systems, and some that are much further out than Pluto, we'll see. But so they're incredibly, some of them are incredibly large, much larger than the solar system. I think I'll show you the record. I can't remember how much bigger it is off the top of my head, but I'll show you in a few minutes. There are many systems that have several planets, and the entire system, it could be contained within the orbit of Mercury. Their stars are much smaller, and but all the planets, some of those planets are about the size of Earth, but they're all be within the orbit of Mercury. The planets themselves have a huge diversity in size, mass, temperature, density and temperature. I made a new word, temperature, the combination of density and temperature, and what they're made out of. Right, we already see, you know, we have rocky planets in the solar system and gas and ice planets. We have to add a couple of more variations to that. Such as water worlds. We have discovered exoplanets that, remember that the ocean of the Earth is an incredibly tiny part of the layer, you know, a couple of kilometers down at the most. These things have oceans that are hundreds, if not thousands of kilometers deep, even deeper than the oceans on Enceladus and Europa. And they're not covered by ice. They're warm enough that their entire surface is liquid water. There are planets called super Earths that are rocky planets, but are much larger and much more massive than the Earth is. Many of the exoplanets we have discovered are what's called tidally locked to their stars, where they are just the way the moon is tidally locked to the Earth, and we always see the same face of the moon. Well, they are tidally locked to their stars. So one side of this planet is always facing its star, and the other side is always cold, always dark. And then we've already talked about the hot Jupiters. These planets that are the size of Jupiter, that there's no way that they could have formed so close to the stars. Their atmospheres are boiling off of them. A new class of planets. Remember, these were the evidence for the planetary migration hypothesis, that the planets did not form in the orbits where they reside in now. They can move around the early chaotic solar system. Remember, we saw that the evidence of that early chaos from an exoplanet system, where we actually saw a planet that was destroyed. That was an exoplanet. The size of the detected exoplanets, if we kind of categorize them, right? Well, one thing we want to see was, well, what's the most popular kind of planet that's made? What planet is made the most in the universe? Turns out that these super Earths and or mini Neptunes are kind of tied. But we have to be very, very careful with this because there's what's called a selection bias. Whenever you collect something and you're trying to extrapolate to what really is, you have to be careful about things that are easier to detect. And one of the things that make things easier, the bigger they are. So, right, if you're trying to find something lost at the beach or whatever, it's going to be a lot easier to find your umbrella than it is if you lost your car keys. Bigger objects are easier to find, even in astronomy. So be careful. The tinier planets are harder to find. So while you know, the Earth-like planets are only a little bit more than 15% of the type of planets that we have observed, they're a lot harder to find. So it could well be that Earth-like planets are, there are more Earth-like planets in the universe than there are super Earths or mini Neptunes. It's just that they're harder to find. And a thing that goes along, which tends to go along with planets anyway, the more, the larger they are, the more massive they are. And one of the techniques that we use to discover exoplanets is by their gravity. And so more massive planets are easier to detect. And also, remember, gravity goes as 1 over the distance squared. So the planets that are closer to their stars are easier to detect by use of gravity anyway. So that is, those are the selection biases that we have to keep in our brains. We have tons of these crazy star systems where all of the planets are within the orbit of Mercury. That's actually the most abundant star systems we've found. They're more likely to be that way than they are what we would call solar. I was going to say normal size, but let's say solar system size. And the ones that are larger than the solar system are exceedingly rare, but those might just be harder to detect. And the ones where the planets are more close to their star, they're going to have a larger gravitational effect on their star, and therefore they're going to be easier to detect. So it's very difficult for us to really, until we get better at this, and we are getting better at this, we are getting more sophisticated telescopes. We have dedicated telescopes to find these things. And so we can find Earth-like planets. When we first started doing this, we couldn't find a planet that was as small as the Earth, but now we're getting to where we can. So this distribution may change. There's a selection bias to this distribution of the kinds of planets. A better way to categorize them than just their size and their mass separately is their density. And for those of you who don't remember your chemistry or your physics, the density, it's on our formula sheet, but let's, I don't need to write it down. The density it's an easy formula. It's just the mass divided by the volume. The mass, it's the ratio of a planet's mass to its size, if you will. And remember that Earth does not have the largest density. Well, it's close to the largest density. I was going to say Jupiter, the most massive planet and the largest planet in the solar system, does not have the largest density. Because it's mostly made out of hydrogen and helium gas, or hydrogen and helium liquid, or metallic hydrogen. So the density actually can tell us the difference between a rocky planet, which is going to have a higher density, than a gas giant, which will have a smaller density. And in between are planets that have about the density of water, which is 1 or 1,000, depending on what units you use. And so we can determine by measuring the density what the internal structure of an exoplanet is. And if you plot that, you just this is actually another way of doing that would be plot the mass versus the size, kind of give you a visual representation instead of a mathematical one. You can see how the different, I don't know if you can see this on your screens right now, but if you look on it in the lecture slides, you can blow it up and you can read the text on here and stuff. But this is the radius, which is a function of the size, and it's in units of Earth radii, and this is the math in terms of Earth mass. So Earth better be 1 and 1. Well, there's 1 and 1. There's the Earth right there. So you can kind of see the green dots here are the planets of the solar system. We have the terrestrial planets down here, like Earth. We have the ice giants here, like Uranus and Neptune, and then we have Jupiter and Saturn up here. But you can see, whoa, I got this whole other kind of class of planets up here. these hot Jupiters and things like that. And then I also have something in between the ice giants and the gas giants. And those are the water worlds. A lot of you used Interstellar for our sci-fi discussion question. Remember on sci-fi, there was a planet in there that was completely covered in water. And those are actually real. There are planets like that. These are the planets kind of in this band here. What about the oldest planet yet discovered? One of the things we want to learn, right? You know, are there planets older than the Earth? Actually, there are. And in fact, this planet is actually a little bit controversial, and it has been in the past. The new estimate for its age is 13 billion years old, which is shorter, younger than the age of the universe before. At one time, there was we used to think the universe wasn't as old as it is now, and we used to think that this planet was older. We had a planet that was older than the universe, which makes no sense. But now, by further study, we've the age of the universe has gone up, and the age of this planet has gone down. It's nicknamed the Methuselah planet. I don't expect you to know the names of any of these planets. Most of them don't have names. Most of them, there's a naming convention where the first name is actually the name of the telescope. So I've already seen, many of you have Kepler planets. That means it was actually, it was sort of named after Kepler, but it was named, that name is the telescope, which was named after the scientist Kepler. And so most of these planets don't even have names. I don't expect you to know the names of them except for the one you already know, right? Proxima Centauri is the only exoplanet I expect you to know. It is the closest exoplanet. But let's look at this oldest planet. Let's look at this Methuselah planet. This planet is so old that it outlived its stars. So another interesting thing I should have said that was interesting, I guess it's my scientific bias, is that many more have them than don't. Many of these systems have more than one star. The 60% of them have more than one star. 60% of the stars that you look at in the sky that just look like a single point of light are actually two stars that are very relatively close together, orbiting each other. And so we can have two stars close to each other, and we can have planets orbiting them. There are a couple where the planet actually, one star has planets orbiting in, and then they both kind of orbit around each other. So you can have, gravity doesn't care whether you have nuclear reactions going on inside of you or not. And so you can have two stars. Remember, Jupiter, it was maybe 100 times more massive, would have collapsed into a star. It was the metallic hydrogen that kept it from doing that. That weird quantum mechanical pressure that kept it from collapsing into a star. The sun, we'll learn next week, went right past that. Even the quantum mechanical pressure couldn't hold together, and it exploded with nuclear fusion. Anyway, not all stars, live the same amount of years as our sun will. There are the dead zombie stars that we talked about first week in class. And this planet is orbiting two of them. So it's got two stars. Both of them have died. Remember, one of them turned into a neutron star and the other one turned into a white dwarf star. We think there is a possibility that this planet formed after maybe one of the planets actually went supernova. The planet that turned into a neutron star, which is depicted here. Again, this is not a real image. Again, an artist's impression using all the scientific data that we know about this system. This star went supernova, And either that planet survived that supernova explosion or was actually formed by the bright, very soon after that planet, that star exploded. I don't think you would want to live on this planet because neutron stars, they shoot out they shoot out X-rays. Sometimes they shoot out gamma rays. So I don't think you would want to live on this planet. Maybe there's some form of life on that planet that loves X-rays. Who knows? Probably not, since it's probably older than that planet, than that star that exploded. Here is the exoplanet system with the largest orbit. So that's 4,500 AU. So that's that's 1,000 times bigger than the solar system. It's a giant planet. Again, you don't need to know the name of this planet. But using Kepler's laws, I mean, you can't quite use Kepler's laws because Kepler's laws, we have to use what's called a modified Kepler's laws now, because we need, remember the mass of the planet doesn't matter as far as Kepler's laws go. Newton's, it's the mass of the sun, right? It doesn't matter what the mass of the object you're dropping is on Earth, but it does matter. If the Earth was more massive, it would matter. The orbital period of a planet orbiting the star depends on the mass of the star, not the mass of the planet. So we will learn what's called the modified Newton's or modified Kepler's laws that have the mass of the star in the calculation. And it's not on our formula sheet. You'll have to do it maybe once or twice for the homework, but you won't have to do it on the final. Okay. So, well, hold on a sec. Let's revisit those hot Jupiters. Here's an actual picture, an X-ray image of this system. It's got two stars, which you would expect to emit X-rays, but the planet is also emitting X-rays. You don't expect planets to emit X-rays, only if they get hot enough to be stars. The X-rays we see from this hot Jupiter are basically its atmosphere blowing away. This thing is so close that it has a period of 10 days. It orbits its star. It only takes it 10 days to make one complete orbit around its star. There's more than a handful of these. Here's just an example of the kinds of hot Jupiters. So you want to write about a hot Jupiter. Here's a list for you to look at. Again, these are not. I'm not going to. This is the last time I'm going to say it. None of the pictures I show you tonight are real, but they're scientific artist representations of them. I would hope maybe sometime when you all teach this class, you'll be able to actually show actual images of planets like this. Unfortunately, not even the James Webb is going to be able to take images like this of these exoplanets. It will be another level of technology that we'll need to be able to actually take an optical image of these hot Jupiters. And as you can imagine, invisible light, the light from the sun, the star they're orbiting is going to overwhelm them. So it'll have to be, you'll have to somehow eclipse that light or take into account and subtract that light out using computers. We're already starting to do that instead of an actual physical object to eclipse that light. You just kind of subtract it out using the computer simulation of what that light should be and see what's left over. There are the super Earths, the Godzillas of Earth. Here's an example. Here's a crazy system that has almost a kind of this is a sun-like star. It has a planet called Kepler 10b, not a Godzilla. Actually, this is still a lava planet. And it probably will never cool off. It's orbiting so close to its star that it's never going to cool off. Its entire surface is molten lava, just like the Earth used to be, but the Earth cooled off. Even Mercury cooled off. This planet is not going to cool off. It is a lava planet and will stay a lava planet. But its sister planet is Kepler-10c, which is a rocky planet. It's 2.3 times the size of Earth and 17 times more massive. I would not want to live on this planet because it's going to be hard to walk on this planet. Remember, the gravity goes as the gets stronger with linear with the mass. So the mass would say you would weigh 17 times as much as you would on Earth, but it's not just the mass; it's the size. This thing is, two times bigger, and so gravity is not going to be 17 times stronger, but it's still going to be whatever 17 divided by 2.3 squared is. You weigh about 2.5 to 3 times more on this planet than you would on Earth. So it would be hard just to walk around. I also wouldn't want to fight anybody who was born on this planet. And we wouldn't want to do hand-to-hand. I wouldn't want to wrestle with somebody on this who was born on this planet because they'd just throw us around, right? They'd be 2 to 3 times stronger just by lifting, being able to walk around on this planet. So that kind of brings me to why, there are, we study everything in the universe. That's our jobs. But part of why this captures normal people's imagination for 2 reasons. These are important. One is to look for other life, right? That is probably the most interesting thing most people find about astronomy is there life on another planet? These are good candidates. These super Earths are good candidates for finding life. Another reason is if the human race is going to survive for billions and billions of years, we're going to have to find another place to live for many reasons. One is just we take up too much resources, and so either our population will just run out of resources and starve, and our population will reduce that way, or we'll find another place to live. Maybe it'll just be a space station, but it'd be nice to have another planet to live on, right? So these are, other than the gravity thing, after a couple of generations, our great grandkids will be fine with that. They'll evolve to live on a more massive planet than the Earth. So just for selfish reasons, to find another place to live. There's also, it's not just us starving to death, right? The sun is going to kill us in about probably about 100 billion years. It's going to actually kill the Earth itself in about 5 billion years. We talked about there may be a comet that kills the dinosaur. We're due for one, astronomically speaking. A massive thing that may not destroy the Earth, but it could kill everything except for whoever's going to take over next on the planet. So it would behoove us to find another place to live. And these super Earths are a good candidate for that. There are the exotic super Earths that are made out of precious metals on Earth, made out of diamonds and sapphires and rubies. When these, kind of a little bit further out than the lava planet, these planets, they're and depending on they're formed in a different a gas cloud that had a little bit more calcium and aluminum in it than ours did. When those things form rocky planets and they get compressed, the diamonds aren't just in this down deep in the core like they are on Earth. They're actually maybe the entire surface is covered in diamonds instead of rocks that we have. There are, you can kind of see all of this stuff. There's olivine and garnets, and this stuff is all what we call precious. They're only precious to us because you have to dig for them. You know, probably they would find a precious thing to them would be coal or something like that. Well, I guess we have to dig for coal too, but you know what I'm saying. A regular rock to a person on this planet would be precious because they're walking on diamonds. They're sweeping up diamond dust in their homes. So these are the exotic earths. They have to be more massive in order for the pressure to actually make those precious elements there. Let's talk about the ocean worlds. These are the super Earths that are completely covered. And remember, the oceans on Earth wouldn't show up on this diagram. They're like a thin layer. But these ocean worlds, instead of having the mantle, right, that on Earth, that Play-Doh or really, really hot baby powder that the continents are floating around on, there are no continents to float, and it's just completely covered in water. They do have rocky cores. They probably have a mantle, just like the Earth, but most of them are basically just water. Hundreds, if not even the thousands of miles down. It's just water. And at least on the surface, they aren't. It's not solid. Could be some weird stuff as you get down. Remember, the pressure and temperature can do strange things. You may say, well, you could have solid water down there that's not ice because of the. I mean, it is ice, but it's not. It's incredibly hot ice because of the pressure on there. Okay. Let's see. All right. So let's watch this video. Sorry, that did not work. Let's watch this video about if we're going to find a place to live, and we kind of like Earth, let's find some Earth-like exoplanets. There are Earth-like exoplanets out there. Let's watch this video about one.
NASA's Kepler mission has discovered the first Earth-sized planet orbiting in the habitable zone of a star outside our solar system. The newly discovered planet is called Kepler 186f and is about 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
Kepler 186f resides in the Kepler 186 system, about 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f, orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
On the surface of Kepler 186f, the brightness of its star at high noon is only as bright as our Sun appears to us about an hour before sunset. Scientists believe Kepler 186f is likely to be a rocky world, but are unable to confirm its mass and density.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
Managed by NASA's Ames Research Center, the Kepler mission collected this data using a space-based telescope to search one part of the galaxy for potentially habitable planets.
All right. So there are a handful of these Earth-like exoplanets that we have discovered. there's a whole lot of stuff in there to unpack. So let's unpack it. First of all, they mentioned the Kepler Space Telescope. This is where most of the exoplanets so far have been discovered, not exclusively, but most of them. It's been up there. It's still up there, but it's not working. It ran out of fuel, so it's just up there orbiting. But it doesn't really transmit. You can't steer, and it doesn't really transmit data anymore. It's now unceremoniously been relished as what we call space debris out there. There's a tremendous amount of stuff orbiting our planet. You can Google that. You can actually see a map of it, see all of the stuff that's not even being used anymore. That's in orbit around the Earth. At some point, we're gonna have to figure out a way to clean that up. More stuff we put out there, it's going to start to be dangerous. It's going to start colliding. It's going to be like, none of you mentioned Gravity, which I didn't like as a movie, other than the destruction piece. I mean, it was okay, but if you haven't seen Gravity, just watch that first episode of how the little piece of space junk can wreak havoc with the space station and things like that. Actually, I like Gravity the more I watch it, actually. I didn't particularly like it the first time, but I mean, it's hard for me not to like science fiction, so it has to be really bad for me not to like it. Anyway, it's been up there since 2009. This thing, when it was working, I mean, I can do it in numbers. It can measure a 0.008% of decline in brightness. So that's basically how this is called the transit method. We'll study it in detail on Wednesday. But it's like a little eclipse. The planet moves in front of the star instead of blocking it all out. It just blots out a little bit of it. And if you can really keep track of the brightness of that star, you can actually see that. This telescope was able to measure a 0.008% decline in brightness when an Earth-sized planet eclipses a sun-like star. The equivalent of that is if you had this telescope on the Earth and somebody lit a match on the moon, you'd be able to tell that it had lit a match. That's how sensitive this telescope was. But it ran out of fuel in 2019 and has been replaced by TESS, the transitioning exoplanet survey satellite. You watch, there's a video on this in our content section. You will see those thousands of exoplanets that Kepler discovered is just if you go out to the night sky and put your hand out like this, that's the size that it actually worked on. Most of the exoplanets it found were in a piece of the sky about the size of your hand. Not literally, but looking at that, right? TESS has 4 cameras, and it spins around, and it basically, it already done this. It's done this. It's taken a picture of 98% of the sky, and it's already discovered 80 new systems with thousands and thousands more candidates. It also helped. It was that second measurement. For many of the Kepler planets, you put, make sure that Kepler was right and make sure this satellite was working, so you would rediscover these exoplanets. So this is our new workhorse, and then these things are in Earth orbit, so you don't have to worry about launch windows and being able to get there. And so there's several other satellites that are being built now to replace TESS. Again, the number of exoplanets is going to just continue to grow and grow and grow and grow. The other thing they talked about in that video was the habitable zone. The strictest definition of a habitable zone is it's also called the Goldilocks zone. I like to add other things for the Goldilocks zone, but one of the definitions, the Goldilocks zone, is whether there can be liquid water at a reasonable enough atmospheric pressure, whether you can actually have liquid water on its surface. As we talked about, liquid water, as far as we know, well, liquid water is required for life as we know it. Is a better way to say that. There could be other kinds of life, but when we define this, we're gonna be human centric. We're gonna look for places that have liquid water on their surface. Now, when you Google, or when you write, or when I tell you a planet is in the habitable zone, that does not necessarily mean that it does have water. It's just that it could have the right temperature based on how far it is away from the sun. You would have liquid water in there. It's in that's what that zone. And as we said, it's interesting to look for other life. It's interesting to look for us to live, a place for us to live. Now, the habitable zone is different for every star because there's no two stars that shine with exactly the right brightness or have the exact amount of energy output. We're going to classify those in a couple of weeks. We'll learn the different classifications of them. We'll talk a little bit about them. Now, you'll read about them when you do your exoplanet. You'll know more what that means. I mean, basically, we classify stars by their temperature is all we really need to know. And then, believe it or not, once we know the temperature, we actually will know the mass and the lifetime of a star. A preview of in the next couple of weeks what we'll learn. So all we have to do is classify them by their temperature, really. But they're all correlated. But depending on their temperature, the habitable zone is going to switch a little bit, right? For cooler stars, you're going to have to be closer in order to not be cold, or to be warm enough for liquid water. Remember, liquid water is a band. If you're too close, your liquid water evaporates. If you're too far away, your liquid water freezes. But we also learned something very important last week. That all depends on your atmosphere, right? So take this with a grain of salt. And in fact, we have 3 planets in a habitable zone, strictly speaking, when we just talk about radiation from our star. Venus is habitable, Earth is habitable, and Mars is habitable. We do know that at one point in all of their lives, they probably had water. We know there was water on Mars. We think there was water even on Venus. But at this point, there's only one. So take this with a grain of salt. Also, you can see here is a Gliese 581 star system. It has 6 planets. They're not all within the orbit of Mercury, but they're all within the orbit of Earth. But the one that's the same distance, or the sort of the same distance away from Earth, is not habitable because Gliese 581 is much cooler. One thing we already did know, we learned in chapter 5 that the hotter a star is, the bluer it's going to be. The cooler it is, the redder it's going to be. This is what's called a red dwarf star, and the planets. There is a planet, Gliese 581G, is smack dab in the habitable zone of Gliese 581. By the way, if you see Gliese 581A, the A is the designation for the star in a star system. Then it goes B, C. The anything higher than an A will be designated the planet. The reason why I kind of close my eyes there is I forget how they designate the stars, whether there's 3 stars. I think it's just A1, 2, and 3, but I'm not sure. I'll look that up for next time. But the A are the stars in these systems. Okay. So that's Strictly speaking, habitable zone is just liquid water. That does not mean that there's life on that planet. It doesn't even mean that there's liquid water on that planet. It just means it's possible. Let's say that. Depending on a planet's atmospheres or maybe something else, you may or may not have liquid water on the surface. So there's a whole bunch of systems that have habitable planets. In general, if you kind of see a graphic on there, the green areas are the habitable zones for these exoplanet systems. Here's that crazy one of my favorite star systems, which is called TRAPPIST-1. This is kind of what got most people, the general public, kind of interested in exoplanets. This was like the first one that got a lot, the first discovery got a lot of press, but then, people forgot about it for a while. But this was actually, I don't know what, 5 years ago, we discovered this system. It has at least 3 planets in its habitable zone, but this entire star system, if you look how it's not even within, well within the orbit of Mercury here, and the planet sizes here are actually to scale. So it's got these planets that are they're all about the size of Earth, but they're all orbiting well within what the orbit of Mercury would be. Its star, however, is much smaller and cooler. It's a red dwarf star, but at least 3 of these planets are in the habitable zone of the TRAPPIST-1 system. In fact, some of them, they may all be, because they are all so close to their star that they are tidally locked. So tidally locked exoplanets, they all have the possibility of having habitable regions, not the entire planet. One side of this planet is going to be extremely hot, right? No seasons, no rotation, no day or no night. If you want to go in the night, you travel to a different part of the planet. The planet doesn't move for you. So one side of this planet is going to be extremely hot. These planets are nicknamed eyeball planets, right? They have a extremely hot thing here, and then you have like kind of the twilight zone, and the twilight zone is where you could have liquid water. And then you have the far side over here where it's going to be so cold all the time that at least from the solar radiation, you would have ice. Now, maybe if you have a thick atmosphere, you could somehow, it would kind of smooth out this region. So these tightly locked exoplanets could have habitable regions. They might even get spread out with an atmosphere. Right? If you had a thick enough atmosphere, you might even get the bullseye. The whole planet could have water on there. But a normal size atmosphere, you would get something, a normal thickness atmosphere, to get something like this. So there are more than I have here. I made this slide, I don't know, 3 years ago, and we've certainly discovered more. There's a couple of dozen of Earth-like exoplanets that you could imagine living on. But here's the problem. They're all really far away, right? 638 light years to 22b. Probably the closest, at least, one of the closest ones to Earth is 196F, the one we saw the video on. It's 582 light years away. This 452b, if you like our star, this one, this is orbiting a sun-like star. It's a little bit more massive. You're going to have to do some weight training if you want to live there, but you got 1,400 years to get there. But actually not. Remember, I mean, for us to conceivably go to Kepler 452b, we're going to have to develop near light speed drive. And if we do that by traveling through space-time, there's 2 ways to get there. One is to warp space-time, which we don't have the technical, that the technology for doing that is actually highly speculative, and it's beyond the beyond our understanding in this class, but it is, we talked about the space-time continuum. Kind of think of, you've heard of wormholes or things like that in sci-fi. They are theoretically possible. You're not traveling through space-time. You're either using or creating a defect in space-time, and you might be able to pop out on the other side of the universe, in a matter of seconds. But a less, although still highly speculative, but a less speculative form of transportation would be for us to develop, close to light speed drive. We can never travel through space-time at the speed of light, but let's say we can get close enough, right? Like in our, and you all did very well on this on the exam, by the way, as a class, probably better than any class that I've ever had. Your travel time here, let's say you could go 99.9% the speed of light. All right. It's going to take you 1,400 light years, but you can divide that by 10. But the more you get going, the more you increase gamma, you could conceivably get there in your lifetime, your time dilated lifetime. Again, imagine you'd never be able to, by the time you called back to Earth and said you made it, right? You're talking about 2,800 light years have gone, not light years, 2,800 years have passed on Earth. Maybe people, by that time we may live forever, who knows? But on a one-way trip, you might be able to make this. But it's going to be a voyage of exploration because, right? You're gonna go there and hope you find something. So here's our. There are some closer ones than this that aren't quite Earth-like, but we have our options, and thanks to relativity, we have a way to get there on at least the possibility of getting there on one-way trips. It's really colonization of the galaxy. It's not going back and forth. Right, taking supplies back and forth because everything's going to change so much for those systems. I suppose you could, but it's not. There's no communicating anyway. Just to kind of show you where Kepler 186 sits in its system, if you're thinking of it as a place to colonize. I mean, I'd rather live on Kepler 186f than Mars, to be honest with you. I mean, I'd love to go to Mars and study it, but it's not very hospitable living there. But we actually have a closest exoplanet that it is rocky. It may well have life already on it, as we kind of pretended in one of our discussion questions. Let's watch this video on Proxima Centauri b. Proxima Centauri is the only exoplanet name you have to know.
In the last few decades, astronomers have discovered thousands of new worlds. Exoplanets of all shapes and sizes orbiting distant stars. But it seems that there was an undiscovered planet hidden under our noses all along. It was found orbiting a red dwarf star called Proxima Centauri, which is our solar system's closest stellar neighbour. The star may be nearby, but it's so faint it can only be seen as a red blur in a telescope. For the past few years, astronomers have been peering at its dim and inconsistent light, looking for the telltale patterns that could indicate the presence of planets. A planet's gravity can physically move the star it orbits despite the size difference between them. As the planet circles, the star wobbles. This slight movement can be detected from Earth as a change in the colour of the starlight. The light shifts slightly towards blue, then slightly towards red, as the star moves towards and away from us over and over. When telescopes were pointed towards Proxima Centauri, they revealed exactly this kind of signal, a cycle of changing starlight repeating every 11.2 days. At first, astronomers couldn't be sure that it wasn't just an illusion, natural variations in the star's activity. But as they returned night after night to the same patch of sky, a pattern appeared that could not be dismissed. From nothing more than a distant blurry light, astronomers have now deduced the presence of an exoplanet, named, for now, Proxima b. We don't know much about what this new world is like. We think that it's small and rocky, probably slightly bigger than the Earth. A year on Proxima b is only 11 days long. It's closer to its star than Earth is to the Sun, but because its star is 7 times smaller than our Sun, the temperature on the surface shouldn't be too extreme. In fact, it could even hold liquid water. Proxima Centauri is much more violent than the Sun. Its stellar flares bombard the planet with X-rays, electrons, protons, and other particles. It may be that this onslaught has long since scoured the planet of any water it started with. Or, like the Earth, its atmosphere and maybe a magnetic field could have protected it. This small rocky planet, sitting bang in the middle of the so-called habitable zone of its star, could be a lot like Earth, which means that Proxima b may not only be the closest planet outside our solar system, but also a prime candidate in our search for life. With current technology, it would take us tens of thousands of years to travel the 4.2 light years between us and our new neighbour. But if we do develop a fast enough way to explore the galaxy, Proxima b could be our very first stop.
So we actually, a couple of things about that. First off, we discovered another planet orbiting that system. So she mentioned a way that I personally like to define the Goldilocks zone is much more than whether it can have water on its surface, is whether it has an appreciable atmosphere and whether it has a magnetic field. I mean, those are the real, that's the real Goldilocks zone. It's not a zone, it's not, but the Goldilocks situation. It takes a lot more, as we've seen even in our solar system, than being at just the right distance. Because again, Venus is not habitable anymore, and Mars is not habitable anymore. So it takes a lot more than that, just that right zone of distance. And in fact, it has a lot more to do, or not, it has a lot to do with the kind of star as well. The other thing she mentioned is that the star that Proxima Centauri b is orbiting is very violent. It's actually much cooler than the sun. It's what's called a red dwarf star. The good things for life about red dwarf stars is they live a lot longer than the sun, but they're very violent. So if you've heard of solar flares, if you haven't heard of them, we will learn about them next week, actually. They can be devastating, especially for planets that don't have magnetic fields. They can be devastating even if you do have a magnetic field. And so many stars, particularly the red dwarf stars, are much more violent than the sun is. But there's actually a type of star that's a little bit better than the sun. And we call these Goldilocks stars. Scientifically, the class is K-type. Again, that just has to do with their temperature. They're a little bit cooler than the sun. They're a little bit warmer than those red dwarf stars. You don't get as much ultraviolet radiation to start with. They're much less violent. They're much less prone to solar flares than the red dwarf stars are. And they live a lot longer too. The Earth, the sun is only going to live for 10 billion years total. And so we've got 5 more billion years to figure out a way to go to one of these these other planets. As I said, it's gonna be worse than that. We have about 100 billion years. 100 million years before the planet basically we lose all our water. Again, we'll talk about that next week. So these K stars are the Goldilocks stars, and there are lots of them. There's actually more stars like this than there are sun-like stars. There's more red dwarfs, but there's it's not like these are obscure. They're one of the most populated type of stars in the universe. And so this would be a good place to look for. And we have found planets around stars like this. And in fact, we have identified 24 what we call super habitable exoplanets. Believe it or not, we think that these planets are even more conducive to life than the Earth is. There should be 24 now. 24 of these planets. They're older than the Earth. They're warmer than the Earth. They're larger than the Earth, so they have a higher probability of having a magnetic field. They're wetter than the Earth. And they're orbiting longer-lived, cooler stars than the sun. A fun fact about these super habitable exoplanets is that, remember, our vegetation is green because the peak frequency wavelength of light coming from the sun is green. That's why the plants are green, the photosynthesis. They can absorb that, they can keep that green light, they use that green light better. So the vegetation on one of these super habitable planets would probably be red or purple, kind of corresponding to the wavelength of the light from their star. So this is where we want to go. We want to find one of these super habitable planets. Now, again, they're more massive, so we're going to have to do some weightlifting before we get real strong. But and we won't have to, if we go to a planet just like Earth, we're going to have to move again in another 5 billion years or so. Okay. She kind of mentioned a preview of next week of the radial velocity method. It turns out that most of these methods, we're actually looking at the light from the star and determining that the planet is there by slight variations in the brightness of the star or in the wobbling of the star. We determine whether an exoplanet is there or not. And that's what we'll talk more about on Wednesday. So that's it for now, for tonight. I'm making up words. Any questions or comments on anything? Okay. All right. Thanks for coming, everybody. Have a good night. Go watch the Bears game. Go Bears. And I will. I'll see you on. I'll see you Wednesday. Take care. Bye.